I had the distinct honor of hearing more about his work when we were talking about UEC. It's going to be an awesome talk. Mike, so grateful for you to join us. And I know you're going to have a very interesting, lots of questions here from a very knowledgeable and eager crowd to learn more about your work. So thank you.
And if you do have questions during the presentation, feel free to drop them while you're thinking of them in the chat, or you can hold on to them until the end when we will open up for questions, and you can turn on your camera and ask them directly. So your choice.
Hi, everybody, and thanks for the invitation. Pleasure to be here, and I've seen some of the previous talks, which have been very interesting as well, and it's particularly great to see stuff being applied, which is not what I see day to day in academia. But I hope that some of the stuff that I present sort of bridges a bit of a gap between just basic science research and something that could actually be useful in the urban forest realm. So let me share my screen. Okay, so the title of my talk was just I was really just seeking a way to be able to talk about two current projects, but tie them together in some way. And so we have one piece of this presentation is going to be about urban trees and cooling, and we talked about this a little bit actually in last month's UEC, so a bit of a teaser there. So that'll be urban trees and cooling in DC, and seeing the effects of partitioning canopy by site, like canopy over paved versus unpaved surfaces, for example, and the impact of tree canopy configuration. So big old patches of canopy versus more individual or distributed little bits of canopy here and there. So that is the paper that is out right now. And so maybe kind of the one that I want to make sure I cover for everybody. And then the more work in progress is the also feel the heat part of the title, which is urban tree phenology. So the timing of when leaves are put on the tree and when they fall off, and how that changes based on tree species, site, and kind of interannual like climate variability. So one interesting way to see how the urban forest is changing, partly based on the urban heat island, and then as exacerbated by overall climate change. So that one I will hit as much as I can. I was wrong about the timing of this talk a little bit, so I will want to make sure that there's some time for questions too. So let's talk about urban trees and cooling, something I'm sure many of you already know a lot about. So the motivation for our work here, to be honest, was largely, well, it was two things really. It's a little strange motivation. One of them was that I needed a COVID-safe field project for 2020, and it seemed like riding my bike around DC measuring temperatures would be a good thing to do. And this was inspired by Carly Zeider, who is at Concordia University in Montreal. Her study, kind of a splashy publication about urban canopy and cooling. And some things that they found were that you needed 40 or 50% tree canopy cover to lead to a substantial cooling effect in the mid-afternoon. And so that's what you're seeing over here in this plot, is how much tree canopy do you need to get over to this 1.25 or whatever degrees of cooling. So kind of corresponds with some other work that also suggests you kind of need these patches, these larger amounts of canopy grouped together to lead to cooling, at least in the heat of the day. Other studies kind of look at the location, so the context of canopy and how that relates to cooling. So is it these street trees that overhang impervious surface that are going to be good for cooling? Or is it more tree canopy that is overhanging pervious surface, or unpaved, or grass or soil or something like that, that's going to do the bulk of the cooling? And so that there's sort of mixed results on these topics, and we wanted to add to that body of literature. So the other motivation for how we conducted this study in particular was the existence of 70,000 plus temperature measurements throughout Washington, D.C. in the one day in the summer of 2018. And this is from Vivek Shandis and colleagues. And they've started to get volunteers to do these urban heat campaigns in a lot of cities around the country right now. I would say we're up maybe over 20 cities. So this is kind of a hot topic, as it were. And what they do is they drive around and collect all these measurements, trying to cover as much of the city as possible. They do it at very early morning, kind of roughly pre-dawn, the heat of the day, so like 2 p.m., and then again in the evening, but before sunset, to see the evolution of the urban heat island. And so that's what you're seeing over here as results from their paper in Washington, D.C., where they've actually expanded, they've modeled the temperature over all places in the city, not just where they took the measurements, using some machine learning magic. And so you can just see the different times of day. You can see, for example, Rock Creek Park being very cool in the afternoon. The heart of downtown is relatively hottest in the pre-dawn hours. So they published this elsewhere, but we said, let's just take that data. We'll forget about the bike data that I collected right now, and just went with this more spatially intensive measurement. So that really gave us an opportunity to look at these spatial covariates, like relationship with paved surfaces, unpaved, and then configuration, just because we had so many sample points. So as I've been alluding to, we wanted to look at the modification of air temperature by urban tree canopy, the scale of analysis, which I won't really talk too much about, it's a little in the weeds, and how that varies how the cooling varies by time of day. That's one of our key contributions. Then the configuration, the site effects, hard canopy and soft canopy, hard being over impervious, soft being over pervious. And ultimately, is it more effective then to cool a city using large forest patches or evenly distributed canopy? So first, a little bit on definitions here and what these different classes look like. So you all probably know the one on the left is just overall urban tree canopy, which I made this layer in DC using LiDAR data and high resolution imagery. There's a lot of good, DC is a really good data city, so this is not too big of a task to get a decent UTC layer. And then using other data from the city, just like roads and parking lots and whatnot and buildings, and so impervious surfaces, partition the canopy into soft versus hard. So you can see it's pretty obvious that there's a lot of soft canopy over people's yards, et cetera, which is in the dark green, versus the lighter green is the hard canopy. So relatively lower percent cover, of course, for hard canopy, but perhaps an outsized importance remains to be seen. And then patches versus distributed. This is Matt Baker's work from UMBC, who was also mentioned in last UEC, of doing some pattern analysis called morphological spatial pattern analysis to basically say, are you a clump of trees that has a core, meaning there's some more canopy even after you travel in 15 meters from the edge. So it has an edge and a core. That's what our definition of a patch is. And everything else that's soft canopy is considered distributed canopy, meaning it does not have a core. So it could be individual trees or could be small clusters of trees. So our modeling strategy, we had basically one model for each of our main research questions. And this is using, it's called generalized additive models. And basically it's just a nonlinear modeling technique. I won't go into the details right now, but it's a way to look at the relationship between a bunch of predictor variables and temperature anomaly. So if you look over at number 1, you've got temperature anomaly as a function of tree canopy fraction plus impervious surface fraction, the interaction of those two things with each other, and then some other things we found to be generally important, but not a focus of this paper, was elevation, wind, speed, and direction, and then over just spatial coordinates. So the key thing here is the stuff that'll show up in these boxes. So model 1 was just tree canopy and impervious, kind of the general way that people do these studies. Model 2 was partitioning into soft canopy fraction and hard canopy fraction and impervious. And model 3 was the spatial configuration. So patches, distributed canopy, hard canopy, impervious. So that's what we'll see the results from. So just to give a basic lay of the land here, what did we find? So overall tree canopy in DC was estimated at 38%, which lines up with what I've seen from others, from Casey Trees, et cetera. So looks good there. As far as our estimate of tree canopy from our sample, from the temperature points, it's significantly lower because it's biased towards roads, because that's where the sampling is taking place. And as in many cities, there is a very strong negative relationship between where there's canopy cover and where there's impervious surface. And so that makes things difficult a bit from a modeling standpoint, because your two key variables are highly correlated. So as tree canopy, as you go to places with more tree canopy, you're probably going places with less impervious surface, almost by definition. Okay, so let me introduce these graphs, because this is kind of the key results here that we're showing. So each of these charts represents the kind of the unique cooling impact of a particular variable. And so in letter A here, you're seeing TCF, which is tree canopy fraction. Letter B, you're seeing impervious surface, and letter C, you're seeing elevation. And on each chart, I'm showing the pre-dawn effect, the afternoon effect, and the evening effect. And so, for example, if we look at the afternoon for just overall tree canopy fraction, you see that, well, actually, that's a bad example to start out with, because that one's obscured the most. Let's look at pre-dawn. You can see pre-dawn is in blue here. And as you increase in tree canopy fraction, you get a small decrease in local temperature anomaly. That means temperature difference between the actual measurement point and some reference station downtown DC. So not surprising, not a big cooling effect in the pre-dawn hour. You get a much bigger effect in the afternoon and the evening. So roughly the same. We're looking at something like 1.8 degrees of cooling between 0 canopy cover and 100% canopy cover. It's also important to note these distributions down here, because this shows you how many of our sample points were represented by each tree canopy cover fraction. So not surprisingly, there were not many places that had 100% tree canopy, and there were many places that had about 20% tree canopy. This was an urban study. So you got to kind of take these big values with a grain of salt, because there aren't that many sample locations. Impervious surface was also important, of course. So in the afternoon, for example, if you had more impervious, you have strong warming as you add impervious surface. And then it sort of tails off at the highest impervious values in the afternoon. And we believe that's because at the highest values are also places where you have relatively tall buildings. And so you have some offset effect that's from shading at that time of day. Now, that effect reverses in the pre-dawn. So pre-dawn, the warming from impervious surface continues to go up, probably because those same buildings are now trapping heat instead of providing shade. Elevation, I just note this because I really felt it on my bike rides all the time, is like the lower you were in the evening and the pre-dawn, the cooler it was. So there's some serious, you kind of notice this maybe sometimes, this cold air pooling effect in these in little valleys, which I just thought was interesting. So now we're partitioning the canopy. So soft canopy versus hard canopy. And I think things start to get interesting now. So if we're looking at soft canopy, we're going to start by seeing what we've seen in other studies. So this is what Zeider saw, and this is what several others have seen, where you don't get much of a cooling effect in the afternoon until you get to about 40% canopy. And then you get this drop off, this substantial cooling effect. Interestingly, what no one has really shown before is you get quite a strong cooling effect from soft canopy in the evening. And so that may be a combination of factors from both increased ability to shade in the evening because shadows are longer, and also kind of revitalization of the ability to transpire, which may have been shut down in the mid-afternoon because it got too hot. Hard canopy, also interesting, but only, is only doing stuff up to about 20% cover because that's the highest value that there was. We see fairly strong cooling in the afternoon, so that shading may be important in a dense urban area, but then perhaps some warming, some heat trapping, which others have shown as well in the evening and afternoon. So let's divide up the world even further here and just look at, or mostly focus on soft canopy, but dividing that up by whether it's a clump or a patch, I'm using those synonymously, versus distributed canopy. And so let me just guide you through these figures here. So letter A is just showing you the distribution of patches versus distributed canopy in DC. And the main point here is that patches are not available in that many locations in the city. So most of our temperature measurements did not have much cover by patches. It's kind of like, unless you're near Rock Creek Park or Fort DuPont Park, there's not a lot of patch cover. Whereas distributed, there are a lot more locations that could get you out to almost 50% cover by distributed canopy. So it's a much more evenly spread out, by definition, type of canopy. Letter B shows you the cooling effects in the pre-dawn hours from both of these. So I think the interesting thing here is that there's some residual cooling from distributed canopy even in the pre-dawn hours. I can talk my speculations on mechanisms later if you're interested. But I'll move on to afternoon, where we're seeing almost nothing from distributed canopy in the afternoon. Not much shadowing available, harsh conditions perhaps because they're not surrounded by their tree canopy friends to help keep them cool. Patches, on the other hand, they can maintain their cooling ability in the heat of the afternoon. And so I think this chart kind of helps to explain what we're seeing in these other results in the afternoon of, well, distributed canopy is most of the canopy up to 50%, and it's not doing anything. So there's this flat spot up here. But when you get out to greater than 50% cover, Well, the only game in town then is patches. And so patches are cooling even in the afternoon. So I think that's one way to explain what these studies are showing. And then in the evening, you get very strong cooling effects from both distributed and from patches. Again, distributed is going to be even better than patches as far as the individual tree contribution of shade to the landscape, because they're actually shading, untreed land around them rather than just internal shading inside the forest. So it's useful shade. So this figure goes back to the idea of the distribution, which I was alluding to earlier, to show that on the left are places where patches have more than 10% cover in a given area. And you can see that there aren't that many blue dots. There are blue dots near Rock Creek Park, blue dots near Fort DuPont, a few other places in Northwest DC, but patches are not a distributed resource. And then distributed are a distributed resource, I guess, by definition. So, what does this all mean then? And, I think one of the key take homes here is that, okay, yes, patches are needed to maintain cooling effect in the heat of the day. Our findings agree with everyone else in that. But what we add here is that these distributed trees can do something useful for us in the evening, which is still pretty darn hot these days and getting hotter. And so there might be opportunities to kind of highlight the unique value of individual trees or small backyard trees or schoolyard plantings for their urban heat island effects in a way that wasn't really known before. So, one thing that resonated with me was the idea of DC's River Smart Homes program, which partnership between Department of Energy and Environment and Casey Trees. And it was originally conceived for more of a stormwater benefit, but now we might add on to that that it's going to help with cooling as well. So some potential future work in this realm that might be of interest to some folks is I'm starting to work again with Matt Baker and Vivek Shandes on basically turning the crank on some of these analyses, but in other cities. And I think our plan is to stick with kind of the mixed deciduous landscape that may go places like between Atlanta and Boston and Newark and maybe over to Ohio. So places that kind of have similar climatic conditions, but different urban morphologies and, different latitude and whatnot, and see if these relationships that we found in DC hold up in other cities. So we might be seeking out some partnerships, partly to contextualize our findings and partly to get whatever the best data is for, for example, the best urban tree canopy data that you have available for Newark. I don't immediately know how to find that stuff. This is just a picture of my bike data that I collected. So the advantage of this was that it was collected over the same route on multiple days in a row. And so we may also look at the temporal variability a little more closely. Okay, so that's how urban trees cool, according to us in this one paper. And I'll spend the rest of the time talking about one way that urban trees might respond to heat is through phenology. So this is part of a larger project that I'm working on with Matt Baker and Josh Kaplan and Sasha Eisenman at Temple University that looks at kind of transpiration as a mechanism for response to heat and also phenology. So the transpiration part is a fun thing involving lots of sap flux measurements and lots of drone flying in UMBC campus. So we can talk about that later if anyone's interested. For now, the gist here, the motivation is that there's rather broad agreement that the urban heat island is driving longer growing season lengths for urban trees compared to neighboring rural areas. So, hotter temperatures, 2 or 3 degrees hotter, whatever it is, are mostly leading to longer growing season lengths. Questions are, will that continue with climate change? Will that eventually reverse? How does that relate to water availability? Is it different in Phoenix than it is in DC, et cetera? So there's a bunch of questions that can still be answered. And then also, when people are measuring this stuff from satellites, are they measuring actual changes in urban tree phenology, or are they measuring some incursion of different plant functional types like turf grass or increasing vine cover, making it look like trees are leafing out earlier, other non-native things going on? So these are not entirely settled questions. So we had access to some high resolution data that would help us address the changes in phenology over multiple years at the individual tree scale over all of downtown DC. And so what you're seeing on the left is the bad image, the Landsat. The Landsat's great, don't get me wrong, but it's a satellite where it has pixel size of 30 meters and repeat measurements every 16 days, which is neither of those are sufficient for measuring phenology or for measuring individual trees. Phenology, you want to be able to capture that basically every day during the spring green up period and fall end of season, because the changes can happen fairly quickly. And you also have to be able to deal with cloud cover, so missing a day here and there. So we've got some of this other cool data here, which is planet scope data. So it's like a bunch of CubeSats flying around the Earth every day, and also giving you high resolution imagery. So 3.7 meter pixel size. 2018 to 2021, at least 50 images every year. And we also have a bunch of volunteers with phenocams to look at things more closely and see if the satellite data makes any sense. So first, let's talk about the on the ground stuff. Also kind of, this plays in, this is a connection to some of the urban forestry nonprofits, and we were collaborating with Casey Trees on this back when Jess Sanders was the head of research there. She's moved on. I believe she's the executive director at Sacramento Tree, whatever that organization is called, Sacramento Tree Foundation. But she helped us get a list of eager volunteers who would host basically a security, like a construction site security camera at their house and point it at some trees and leave it there for as many years as they were willing to do so. And so we distributed about 20 of these phenocams, either suction cupped inside of people's windows, looking out at some trees, or sitting up on this highly scientific cinder block creation, looking out, whatever the best angle was to see the most trees. So this thing takes pictures every day. And we'll show you some of those. So here's what you're seeing. So this is one person's view angle. And this is start of season in 2020. And you're seeing daily photos of the green up from someone's living room of 3 crowns for which we know where they are and what species they are. So these are like Chinese elm and maybe a hackberry or something. So this is another example. This is looking at end of season. So this is October to January of 2020 from my high school buddy's roof in Capitol Hill. And he's got the best view angle of all, really, and sees a bunch of maples and a couple other trees there. So kind of fun. And so how do you convert this information into actual usable data that looks at when the season starts and ends? It's a little bit of a manual process, but that's why we have grad students who can go in and basically draw circles, draw regions of interest in around every tree that we think we can identify. And then we magically extract the color data from these trees. And the color data can show us curves, give us some curves about, greenness. It's basically, if we look up at ROI number 1, here you're just seeing, this is just the fall, looking at day of year, and you just see greenness getting less and less and less and less, to the point where the tree is probably red. So peak of redness happens right here, and then the leaves fall off and it returns back to more of a gray color at the end of the season. And so then you can calculate like some metrics from this, which I'll show in a second. So some ways to measure this, phenometrics, one might say. There's a bunch of these, but I'll just talk about the key ones. Start of season. Basically, it's like, when are some amount of leaves on the tree canopy? There's a bunch of ways to measure this. Here you're seeing just 3 different arbitrary points in time where you can say, this is the day of year that we're saying start of season happened. So for example, it could be when 15% of total leaf out happened, or it could be the steepest part of this greening up curve, a little bit of calculus there to measure that. Or it could be the maximum greenness. There's, it's sort of like you just decide on a metric and then use it across the board consistently. Then you want to also look at, when does the season end? This is a single tree, by the way, I should say that, where we're looking at kind of a baseline in the winter, the green up, the growing season, and the end of season based on the greenness of the leaves. Once you have start of season day of year and end of season day of year, you can then, through a little subtraction, estimate your growing season length. So those are kind of the key factors that we might be interested in. So let's look at some of the data that we got from these CubeSats. So just a little closer view in here. This is March 5th. So keeping in mind, in remote sensing world, we make everyone confused by making vegetation red, false color imagery. Sometimes I don't know why we do that, but we do. So vegetation is red. You can see the grass in many places is already green/red, but the trees are not. And you can start to see them green up in April 1st. April 13th is really where the action was happening. 2019, stuff greened up very quickly based on the warm temperatures. And May 7th, everything is fully pretty much leafed out. And you can see how we have a very nice view of individual tree canopy. Also, the other nice thing about working in an urban area that is, gives us some transferable results to non-urban areas too, are just the wealth of other ancillary data. So this is our huge win here is UFA, Urban Forestry Administration data, has over 160,000 street trees that are well positioned and labeled with species. So this is where we can really say interesting things about like species variability and site variability of the trees and how that will relate to their phenology. So thanks UFA for that. So we turn the crank on some models, we extract a bunch of data from all of these tree crowns, and this is kind of the basic thing that pops out. So let's see, we're just down below here, we're looking at one tree. This is a single American elm over 3 years. And you're seeing day of year on the x-axis and a measure of leafiness, NDVI. It's a vegetation index, but basically a leafiness index that shows you when start of season happens, around day of year 110 or so, end of season, and the changes up between the years. So, one thing that kind of can pop out visually here is just how quickly green up happened in 2019 based on the steep slope of this line compared to 2020, which is a much more shallow slope. And that can partially be explained by kind of interesting temperature patterns in 2019, where things started, March was hot and April was cool. And so the green up process started early, but took a long time. So that's, one of those things you could examine further with this data set. Here's the fancy maps that pop out. And so we have individual tree scale start of season. This is just for 2018, looking and colored by day of year. And so, you can see the bottom of Rock Creek Park here coming through. And, the key thing that pops out here is just that there's a lot of grass, and the grass is the thing that has the early start of season, and the trees generally have relatively later start of season. So since this is such high resolution data, you got to zoom in a bit here and see to see the more interesting stuff. And so you're seeing on the bottom is just a land cover, high-res land cover map, where you've got buildings, impervious surface, and then grass in light green and trees in dark green. And so you can see more clearly here, this is a Mount Olivet Cemetery over a lot of this red. And then the National Arboretum is a lot of this blue. But you can still, there's still a lot of variability per tree also that we could boil down into some analyses. One more pretty picture. This is back towards Rock Creek Park and Piney Branch tributary. Just showing, now we're showing end of season. So day of years in the October, November range here. So, don't have much to, I don't have reasons for all of this stuff yet. It's just, it's a starting point. As is this. So just kind of showing, okay, we got a bunch of species, and how do we start putting together this data to say interesting things? And this is just kind of a very descriptive depiction of growing season length on the y-axis by key species on the x-axis, colored by year. So the main thing that pops out here is across all species, growing season length was a lot shorter in 2018 compared to 2019. So red versus green. There are reasons for that that are sort of speculative at this point, but there is also interspecies differences that could be sussed out by site or by mechanism with further analyses. So just to orient you, you've got things like Acer. These are the 4-letter species code, some Acers, a bunch of oaks. These are just a lot of the common species in DC based on the urban forestry data or UFA data. So I'll show you two little analyses that we've started to try to get at some of the mechanisms driving changes in start and end of season. So the question here is, how does end of season vary as a function of air temperature variability? And so we're actually using the Shandis, that CAR data that I talked about for the previous study, to as a data layer for local temperature anomaly. So where is it hot and where is it cold? And we get a little sciencey here on some of this process, but the basic idea is that if you look over on the left, you're seeing the sensitivity to air temperature by species. And so for across all tree genera in 2018, end of season gets 1.8 days later for every 1 degree of increase of temperature. So that's this red line. And then the red boxes are the species variability. So, there's a mean effect. Air temperature pushes end of season later, but there's also plenty of species variability that would be interesting to unpack. And you can see the same deal for 2019, but the effect was even greater. There's also an elevation effect, which I'll largely ignore for right now. So yeah, temperature sensitivity varies by species. You might wonder why. And so this is where we dig one step deeper. say what are some of the key differences that might, based on previous work and theory, might actually drive this, drive different species to respond differently to temperature, and by extension, other site differences like prominence of impervious surface in a given area. And so we started to look a little bit at like plant-water relations. So basically, are you a plant that is constantly bringing up water through your xylem to maintain consistent kind of leaf water content? Or are you shutting down when it's super hot out in order to save yourself from a xylem cavitation, or to be better about your water use efficiency? These kind of things relate to the structure of a plant's xylem and this idea of isohydry. So the kind of the key take home here, or one thing to point out, is that plants with different isohydric or anisohydric tendencies, i.e. those that want to strictly control their water flow versus those who just kind of let the water flow, have different end of season dates and different sensitivities to temperature. Excuse me, I should rephrase that. Temperature has a greater impact on certain species as far as when their end of season comes around, based on how a plant regulates their water. I know it's a bit of a mouthful here, so I'll just show. If you look at this chart, you just see there's a lot of big responsiveness to temperature in the species at the top and less responsiveness to temperature at the species at the bottom. And these are ordered by their tendency towards regulating their water flow. Oaks up here don't regulate much, they let the water flow. Elms and like some tilia, they do more regulation and thus are less sensitive to changes in temperature. So this is a little bit preliminary, but this is kind of the getting into the mechanisms, and we'll work more to see what other things like leaf morphology also play into these sensitivities. So finally, the upshot here is we have a cool data set, always looking to raise more questions and have people say, what wouldn't it be interesting if you could look at this? Because I think we're only scratching the surface here. So we'll work in the future to kind of get better ideas of what urban biodiversity represents and what you can say about it compared to coarse resolution analyses using this sort of information. So I will leave it at that. So we have some time to chat. So thanks for your attention.
Amazing, Mike. Thank you so much. Round of applause. Really great work here. Just going to go through some of these questions here that came up. I think there was a request here for a link to one of your papers. I don't know if you're able to provide. Oh, there we go. There's one of them. Question on what do you use to measure temperature?
Yeah, the temperature measurements are, let's see, I can show it here. So in the bike version, you can see in the bottom right that there is a box that has a data logger in there, and then a cord goes up through this pipe made by my dad in his COVID friendly project. And then there's a thermocouple in this radiation shield. And so it's both protected from sunlight and well ventilated because we're constantly in motion. And so this is essentially like, yes, this is the bike data, but it's basically the same idea as the car data, where there's just one of these pipes hanging out of a car window, like a meter above the top of the car.
So I invite people to raise their hands or drop comments or questions for Mike in the chat window here. just scrolling through, there's one question here. Are you able to see how far outside of a patch the cooling effect happens?
Yeah, it's hard. It's hard to do. And I think that might be one of those things where it would be useful to have data over a lot of days, be a little more focused, I guess, because it's so variable depending on wind direction and magnitude. So I did notice some of that. Like you could sort of see that if you were if you were like northeast of Fort DuPont Park and the wind was going up in that direction, then yeah, that was a lot cooler than it was when the wind was going in the other direction. So it's a little tough to generalize, but other studies have found, anywhere between 500 meters to a kilometer was sort of the magnitude of this park cooling effect. But it also depends on how big the patch is. So Rock Creek Park is going to do a lot more for cooling a larger area around it than like an urban like Franklin Square, one of these a little 1 block square in downtown DC. So there's a lot of variables involved.
A couple of questions here about temperature collection. Just if you could talk a little bit more about that, how the temperature data is collected for the first paper, how you're getting specific temperatures. I know it was done here in Boston with the Museum of Science a couple of years ago, and I think there's a lot of, I'm looking at this map here, there's a lot of interpolation between ground truth temperature and then satellite data, or whatever it is.
Yeah, so for us, for our study, we just used the actual temperature point data. So it's basically 9 cars were driving around the city, all within a 1 hour period to minimize the effects of just like, changing cloud cover or changing other meteorological conditions. So they're rolling around the city and they're collecting data every second. And it's just temperature, just normal temperature. And then at the end of the day, I normalize that. I subtract out temperature measured at the same times from some reference stations in downtown DC. And so most of the anomalies are negative because most places are generally a bit cooler than the reference stations. And then looking at the actual maps on the right, we didn't use those in our study. But yeah, that's an interpolation, basically using some other, it's land use regression. So it's basically taking the point temperature measurement and then spreading them out into a continuous surface using information about land use which is spatially continuous across the whole city. I see Clara has a hand up.
Yep, Clara, go ahead.
Yes, it's in connection to what you're responding to about the temperature here. I'm curious about the slide that had the red representation of the houses when you showed the temperature varying from like April. That specific slide, I was just curious how you got, I know you're talking a lot about temperature, but how did you get those pieces on a monthly basis? No, just a little bit higher, maybe 28.
Oh. Wait, sorry, the houses as red?
Yeah, slide 24, 25, 26.
Oh, these,
27.
Yeah,
that's
oh,
really
these,
how,
okay.
Yeah.
So this is the magic of CubeSats now. So it's planet.com is the vendor, and they become kind of a hot geospatial business because they can monitor anywhere at any time at high spatial resolution. And so you pay them money and they could give you imagery over your study area at a daily time step. So when you're just like doing a little study, I'm weirdo in their world. Like they're used to, you know, doing larger areas or like tracking movements of ships over oceans and stuff. So I'm only doing a 35 square kilometer area. And so it's not that expensive. And I can just ask for a lot of time steps and get a lot of good data. Now, I should caveat here that what I'm showing you here is 0.8 meter resolution data from their SkySat satellites. And this is what I wanted to use originally because it's super awesome as far as the resolution. But there's for various other remote sensing reasons that I can talk to anyone about if they're interested. It was easier to use 3.5 meter resolution data from the same company because it was more consistent. So it doesn't look quite as cool as this, but it still gets individual tree scale information for most crowns.
Thank you. Can
Sure.
I ask a follow-up question since I'm still on the floor, if it's okay? Just about the schoolyards, do you have any additional resources around that? I'm really curious around the impact of like the soft surface tree canopy and you know, its impact on the cooling. Do you have additional resources that you used to do that analysis? I hope that question makes sense.
What do you mean by additional resources?
I guess you mentioned that, you know, having patches like, you know, thinking of things like schoolyard plantings are actually good, looking at their impact on the heat island effect because of how you're planting in those schoolyards of a soft, I think you're talking about soft canopy versus the hard canopy. So I don't know if I missed that point. Maybe it was just a you know, a passing moment.
Yeah, it was. I mean, the schoolyard was just schoolyards and backyards were just my example of places where I've seen people plant some trees, right? So there's many different places where that could happen. But I guess the broader point is that it's very difficult to plant a new Rock Creek Park, but it is fairly easy to get together Casey trees and some schools and plant some trees in a schoolyard where those are going to be distributed trees that are over grass, and those are going to be useful for cooling in the evening hours. So I don't have any further detail about the specifics of, you know, backyards versus schoolyards or anything like that. It's the idea of being able to find spaces to plant in more places and discovering that is in fact useful for evening cooling.
Thank you. I'm curious because
So-
I plant with school, so thank you so much.
Well, great.
Yeah,
Keep doing it.
It's a great question. Mike, if you don't mind just going to your last slide for a minute. I believe you had your contact information. We'll just leave that on the board if anyone wants to capture Mike's email. So appreciative of your time. It is 11 o'clock, so I wanted to give people a chance to depart. And Mike, if you wanted to stay on, defer to you. But we'll be meeting again next month. We'll be hearing from Deanna Moran from the Conservation Law Foundation. She'll be talking about tree ordinances in different municipalities. So I hope you can join us then. I believe it is October 20th, if I'm mistaken. So have a great September. And we'll see you next month.
Thanks, everybody.
Thanks everyone for coming. Thanks, Mike, for presenting.